Hello students, this is the fourth lecture on the course of mechanics of machining. In this lecture, I will be talking about the tool geometry. In the last lecture, we discussed about the types of chips. You remove the material in the form of the chips in machining. And who removes that material? A cutting tool. So cutting tool is very essential and we have to understand the geometry of the cutting tool. Geometry of the cutting tool is very important and it has large bearing on the performance of the machining. Earlier, making the proper tool was considered as an art. You know, some craftsman will make his tool in such a way that he will be able to accomplish good amount of machining, whereas some other person he will not be able to make that type of tool. So earlier days it was considered as an art because it is not very obvious that any type of tool will function. You have to give proper angle to its various lines and surfaces. So therefore it is very essential. Before about 1950s, some research papers were published in the machining, but they did not even mention proper tool geometry. So it becomes very difficult to infer that what forces they should have got and what are the issues. But now there is a standard system. In fact, there are 4 popular standards of defining the tool geometry. We will discuss all of them. In the workshop course, you must have got some exposure about the tool geometry, and in most of the books on workshop technologies, they mention only the American system of tool geometry, but here we will see other type of tool geometry, and in the subsequent lecture, we will also discuss that how this can be converted, that means conversion from one system to the other system. So this is a typical lathe tool. In this is a shank, this portion is a shank, then this is a cutting edge, it is a primary cutting edge, and this is secondary cutting edge, auxiliary cutting edge we can say, and in between there is a nose radius. And you are seeing that suppose I put it on the lathe machine like this, then the job is moving in this direction, that means job is rotating and relative velocity is vertical. So this is relative velocity vector. So perpendicular to that we can say that it is a reference plane. So one plane is this, and then so one direction is this one, vertical z direction, and then the tool is actually moving, traversing like this, that means in feet direction. So that means feet is in this direction and radial depth is actually in this direction, that means towards you, that it is coming. So this one is a typical cutting tool. Now we will trying to understand its various type of angles by means of the figures, 3D figures and 2D figures. This topic may appear to be difficult for some people because you have to realize the 3-dimensional geometry, and many people face difficulty in understanding the 3-dimensional things, but we will try to make you understand these concepts with the help of some figures and visual aids. Now just going to this one, this is a simple that cutting tool. It is showing the cutting of composite by a single point tool. Here this is a cutting tool and this one is a basically perpendicular to the plane of this screen. There is a that cutting edge, and this face is the rake face on which the chips will slide. In this type of tool, rake face is actually this because the chips are flowing here, and then this is a flying face. Rake face and flying face, they meet at some angle, and this makes some included angle of the cutting tool. So in this particular case, flying face is really this. This is the rake face and this one is the flying face. Okay. Now here, this is the cutting speed direction. Cutting speed direction is this. Machine surface you are making it here and this. Then I am showing now a 3-dimensional view of the cutting tool. Here cutting tool may appear it is just rectangular type of shape. If you see the top surface, that is rake face, we can see in that two edges are meeting. So this one is a cutting edge and this one is also a cutting edge. This may be primary cutting edge, this may be secondary cutting edge. So secondary cutting edge, primary cutting edge, then there is a rake face on which the chip slides, and because of the abrasion of the chips etc., there may be, and even temperature is also very high. So wear phenomena, we will discuss these things in detail, but you are seeing that there is some crater type of wear. Crater means a type of pit you have got on the rake surface. So that type of thing is shown here. And then there is this surface is the frank face. Also it is called clearance face. So this is clearance face. Now on this surface is that surface which may rub against the machined surface like that. When you are cutting like this, it may rub like this, and that is why on this you also get some wear, that is frank wear. And these are the, so you are seeing that here, because of the wear some material will be removed and you will get exposed to another type of that edge, that is called basically worn cutting edge. So these things are there. Now again this tool is in my hand, but still I have made it on in the screen a typical lathe tool I have shown here. In the typical lathe tool there is a shank here, then there is a primary cutting edge, and this is auxiliary cutting edge, then this surface downwards is auxiliary frank face, and this one is the principal frank face. Then we have got principal cutting edge, that is doing the main cutting operation, and the tool is actually maybe feed is given in this direction, that is the direction of the feed. Okay. So feed is in this direction as I have shown by the red one. Depth you give in this direction, and that is if you see from the top, then you will see that this type of surface, rake face is very prominently will be visible, and cutting speed is actually like this, vertically upward. So this is the thing. So this surface is the rake face. Rake face is very important. Rake face you can see here, and this one is the nose. Two cutting edges are meeting at some nose. So this is the typical tool. Now if we make the three views of this cutting tool, it will be very nice, we can understand. So three views of the tool, they are shown like that. Top view is actually this nose radius, and this one is there, and front view is this, and then we have got a side view. Now here this is the top view, and you can understand that the feed direction may be here, that means it may be feed. Feed direction I have shown, feed is this way, so it is like this, it is going this way, and naturally this direction is the depth direction, depth direction, that means depth, or radial direction, we can say radial. Okay. So radial direction is this, that means tool may be moving like this. So here in this case, now we can understand the angles. In ASA system, we just define based on these three views, we can explain the angles very nicely. Only we can take three views, three orthogonal views, and we can explain. We will try to understand according to American standard system what are the tool angles, and this you see very carefully. So coming to the top view, that means this view top, okay, top view are okay. So in this view you are seeing what? You are seeing that this cutting edge is actually a bit inclined, okay, to the direction, from the direction of, it is not really totally perpendicular to the feed direction, it is inclined, and this angle is called side cutting edge angle. So you are having side cutting edge angle, that means it is, this may be inclined, it may be 5 degree or it may be some other degrees, 10 degree, depends on that. Of course, it can be 0 degree also. That means cutting edge is perpendicular to the feed direction in the top view, and similarly here you have got end cutting edge angle. Okay, and then so side cutting edge angle, end cutting edge angle. So two important angles are seen in this view, and then you have got a nose radius. They are moving this one. Typical nose radius may be about 0.2 mm, it may be 0.3 mm, 0.1 mm, like that. So these two angles are shown here. Then in the front view, that means if I just put it like this, maybe the front view you are seeing like this, and in this, if you see that this face is moving downwards, that means it is slanted. So then you have got, that is back rake angle. This is the carved back rake. It is also carved, instead of back we can call it top. We can say top rake angle, and this is the rake face, this face is the rake face, and in this you are showing that angle that is called back rake angle. So we give some slanting type of thing. In this position it is called positive rake angle. So positive rake angle is there, negative means the surface will move up as you go from left to right. So this one will be there, and then so in this we are getting one back rake angle, another angle we are getting here. This surface, that means this that surface, you see that this one is slightly inclined. Okay, so that means this surface, this line, if you see that it is in this plane also, that means auxiliary flank plane, this line is not really vertical, rather it is having some type of inclination. Why? So that the tool should not rub against the workpiece. So that is why you are having here that there is end relief angle. So we say that it is end relief angle, and it can also be called, instead of relief, it can be called clearance angle. Clearance angle. Relief and clearance means basically both are the same thing. Clearance is provided so that there is no rubbing of the tool against the workpiece surface, and relief also is basically the same thing it converts, and that is why that it is shown as end relief angle. And then this angle is also really very, very small, maybe 2 degree, 3 degree, 5 degree, those type of things we will discuss. And what is here that angle between these two, this one of course it is not the part of SA system, but naturally you can find out that this can be called as some included angle here. So this is the angle, and really you cannot give that very large back rake angle and very large end relief angle, otherwise this portion will become very thin and then the tool will become weak. So here we have shown in the front view now again two angles, and that is back rake angle, and then we have discussed end relief angle. Now let us come to the side view of this tool here from the side. So if from the side if you see, then you will see that this is the main that notch portion. From here this surface will be slanting on this surface primarily, because cutting is only by side cutting edge mostly in the lathe. So this is more important than even the top rake angle. Instead side rake angle is more important. Chip flow will take place on this one. So this is slanting down, so chip flow will take place on this rake surface through that side rake angle. And then if we see that another flank, this one is also inclined in the other direction from the side, so this you get side relief angle. That means it is here, otherwise this one. Tool will rub, that is why this is shown as a side relief angle here. It is side rake angle, and you have seen this one. So two angles are shown in the top view, two angles are shown in the front view, and 2 angles are shown in the side view. So we have got total 6 angles now here. They designate proper tool geometry, they will be influencing more, and this is the primary cutting edge and it is secondary cutting edge, plus 1/7 element is the nose radius, that is also shown here. It is visible in the top view, that means this is a type of the nose radius, and that is showing the effect of, it also has effect on the machining performance. This is how it is shown. So it is I hope that now you have understood nomenclature of the tool in ASA system. I can illustrate it by means of a bigger object. Say for example, I am taking this book, for example this one, and I am trying to explain you that how 3-dimensional things comes into picture. Suppose this is a book and it has got this type of surface. You see that it has got this surface, this one is there, and then on the bottom another surface is there. In this case both the surfaces are at 90 degree. I can say this bottom surface which is resting on my palm as the Frank's face, and the top vertical one, that means in which the title of this book is written, it is considered as the rake face. So both the faces in this case are perpendicular to each other, but you understand that this is the rake face and this is actually the Frank face, and both the faces are meeting at one edge, this edge, that sharp edge is called cutting edge. Okay. Now what happens that this one, it is cutting like this. Suppose I cut, of course if I move that this book on the my palm, then some portion of the chip will naturally, material ahead will come out of the form of the chip and it will slide on the vertical surface. That means chip will be moving on the rake surface. It may have some resistance, so therefore better to incline it towards this, that means positive rake angle side, so that the chip can easily move. If I incline it in the other direction, then in fact it will be compressing the chip, so it will have even more difficulty to move on the surface. So if I increase the rake angle, my easy movement of the chip can take place, and this is this one. But now in this position, suppose I am moving this one, at my palm there is a lot of friction, so it is not moving properly. So it is better to provide some inclination also here, then it can actually do only proper cutting, but this surface will not be rubbing against the machined surface or against the surface of the workpiece. So that means we have to give the clearance angle, at least these 2 angles, that means rake angle and clearance angle I have explained here. So I have inclined it like this, but if I also inclined like this in the other direction, then that will be called top rake angle. That means you have got a surface can be inclined this way and also this way. So then it gives a totally 3-dimensional type of picture. That is why it is you have to understand that in the top surface is only one rake surface, but you are having side rake angle because it is tilted in the side direction and it is also tilted in the top direction like this. So that is why you are having the back rake angle. That means it is tilted in one direction and it is also tilted in the other direction. So you are getting this one. So this typical thing that you always understand. And now in ASA system, we define nomenclature of the tool is called tool signature. So we have got the tool signature here. Now in the tool signature wise, we have proper system, we have designated again and again. I may not say that which is what angle, I will just say that my tool designation is this, and I will write 6 quantities separated in the form of dash, and you will understand that which one means what. That is called tool signature. So first thing is that back rake angle, second thing is side rake angle, third one is end relief angle, and this delta is side relief angle, and then end cutting edge angle and side cutting edge angle, and another one is the nose radius in mm. So that means this is the thing. So if I can designate in various ways, I can suppose I can write, say suppose 1 and then -1 like that, and then I say 3, then I am giving 5, and I am giving 15, and I am giving again 15, and I am giving 0.2. So if I write like this, you should understand that here the back rake angle is 1 degree, side rake angle is actually -1 degree, and then relief angle, end relief angle is 3 degree, side relief angle is 5 degree, end cutting edge angle is 15 degree, side cutting edge angle is 15 degree, and nose radius is 0.2. This you can understand by this one. So this is ASA tool signature. Now I am coming to the next one. But it is ASA tool signature system is not the only one. There are other systems also, and there are other 3 more popular systems are also there. We must discuss, because some researchers in research, maybe people find convenient to use other type of tool point reference system, because it tells nicely that how the chip is flowing in that particular plane, and this one is more convenient American system from the machine point of view, that you know that because one plane is in the feed direction, other plane is in this direction, cutting direction, like that. So in general we will understand. So first let me discuss general orthogonal system. In the orthogonal system, we make tool point reference system we discuss. So what we do that, we assume the cutting velocity as a datum. There is a relative motion between the job and tool that is designated by V, it is denoted by V. This velocity vector is there. I can take one plane, for example here the blue plane pi r, that can be written as pi r, okay. This one is pi r, actually this plane is pi r. So this plane, that blue one, is perpendicular to the cutting velocity. You very well know that a plane is characterized by its normal. If I tell normal to the plane, that means I understand the plane. Suppose this is the book, and in this you draw a normal to the plane, normal, this one, this is normal line, then this becomes that designation of the plane. So cutting velocity is there, perpendicular to that you take a plane, and that you are calling as the reference plane. Then having made reference plane, I have to make other orthogonal planes. So I take another plane that is which is containing the cutting velocity vector in it, and also the cutting edge. You see this cutting edge is there, that is contained in this thing, and this plane is perpendicular to the reference plane. So this one will be called cutting plane, that is second plane. Now third plane I take simply orthogonal to the other planes. That is why this system is called orthogonal system. So in these planes we can understand all the angles. We have got reference plane, we have got cutting plane, and we have got orthogonal plane, and tool is kept here. You are seeing this here. Now we have another system of nomenclature. This is one I told ASA system, I told ORS system. Then there is one more that is called oblique or normal reference system. In this what happens, reference plane is as usual the same. That means reference plane, it is not changing. In most of the cases reference plane is basically same. It is perpendicular to the cutting velocity, and then we have got the cutting plane. Cutting plane is containing the velocity vector, and it is also containing the cutting edge. That one is there. It is orthogonal to pi r. But the third plane is not orthogonal to other two planes. It is not pi o. Instead it is pi n. It is what type of plane? It is normal to the cutting edge. That means cutting edge is perpendicular to that. So sometimes pi n may coincide with pi o, but sometimes it may not coincide because cutting edge itself is inclined. Suppose cutting edge is inclined, then from the velocity direction, cutting edge need not be perpendicular to the velocity vector. So in that case you are getting that pi n, and this one, that means on this particular plane, so intersection of pi c and pi n will give you a line, and this line is making lambda angle from the velocity vector, because these two are not meeting, these two are not orthogonal, so it will not coincide with the velocity direction. So this is lambda. Lambda is called the inclination angle. That means cutting edge is inclined with the direction of the velocity. That means cutting edge is not exactly perpendicular to the velocity vector. That is why you are getting inclination angle. So this is lambda. This happens in the normal reference system. Now what is the significance of the reference plane, that I will be explaining. Significance of reference plane. As I said, reference plane is actually normal to the cutting velocity. So suppose you have got VC and then you have perpendicular to this is one plane that is called pi r. This is reference plane. Okay. And here the cutting tool is just kept here. So from here you are measuring the rake angle. This becomes the top rake angle. Now what happens? Well, if suppose feed velocity is also there, tool is getting feed in this direction Vf, in that case you can get a resultant velocity. So if you draw perpendicular to the resultant velocity this line, this is denoting equivalent reference plane. That reference plane based on the equivalent velocity, to be very precise, you can measure that way, and in this you see rake angle has changed. So that means it is up to you that you can always decide this one, but most of the cases, cutting speed is much more compared to feed speed. So that effect is very negligible, and that's why most of the cases we find it appropriate to take the reference plane based on the main cutting velocity. That means suppose my tool is moving on the lathe machine like this, then naturally we can have this type of phenomena. Here horizontal plane, if it is moved, can be called as a reference plane because the cutting velocity is vertical. Feed velocity is very small. That effect I am neglecting. That can be always done in this way. So this is the significance of the reference plane. And there is one question often asked, that what is the effect of the height of tool on rake angle? Suppose you are machining in a lathe machine, usually you mount your tool at the center of the workpiece and it does machining and produces cylindrical surface. I can move it a bit above the center line, or I can keep it a bit above the center line. In both of these cases, it will no doubt make the cylindrical surface, but angles will change. That there is a significance of that. What is that significance? That is illustrated it like this. Here, that suppose I have moved my, suppose reference plane I am considering horizontal. Now I have moved my tool a bit down. In that case, my reference plane has become like this, because my tangential velocity here is like this, and you can see the reference plane is perpendicular, and this reference plane is in fact, in this way it is showing that it is coinciding with the rake surface. So that means here really there is no rake angle. That means rake angle virtually has reduced. Earlier the same tool, if it was here, then it was having some rake angle. This is how that it was going. But now I have moved it down, so it is like that. And if you see that earlier there was less gap between the surface and the flank surface, now here this angle has increased. That means relief has increased and rake has reduced. Rake has reduced, so that means somewhat less easy flow here of the chips. This is, I can illustrate it like this. This is a job, and I can say that here if it was at the center, some tool if I mount, then I am observing that it is like this. That is one thing. So here naturally the velocity is tangential. Since the velocity is tangential here, so naturally here I have got that plane here. So you see we have some particular rake angle and we have got relief angle here. This is the relief angle. But if I do like this, same that tool like this, but I am mounting it a bit upside, suppose this time. So since I mounted it upside, I am showing exaggerated, and here it is like this same way. And if I am doing like this, now here the velocity is in this direction, tangential, so perpendicular will be in this direction. So you see that this angle has increased. So effectively the rake angle has increased if you mounted it up, but the more rubbing may occur because the relief angle has decreased. So that means if you move a cutting tool in the lathe above the center, then the rake angle, positive rake angle increases, but the relief angle decreases. And if you move the tool downward, then the rake angle decreases, but the relief angle increases. So you understand that the measurement system is usually based on the reference plane. In most of the cases, of course, we keep the tool horizontal and at the center. So therefore, your cutting velocity is exactly vertical. If it is at the center, because at the center the velocity vector is vertical, it is not inclined this way or that way. So that is why in most of the cases we think that just you take the horizontal plane and that becomes the reference plane and see that surface is how much it is inclined from that horizontal plane. That is why we do that in American system, but in general it is not like that always, that if our referencing system and our measurement system will change if I move the tool up and down. So this tool, cutting tool angles, that means it is not that a particular tool is there and therefore all these things are fixed. The way it is mounted will also change, that it's a geometry, that way it is mounted. Tool is same, this is the tool, but I can have it inclined, I can do this thing. That means on a tool holder, I can mount it in such a way so that its tool angles can change. That point also has to be kept in mind. Now, so we have shown here that significance of reference planes, effect of height and of tool on rake angle. Then I now discuss, there are in fact 4 type of nomenclature systems. Just now I have told only one, that is American system. In the American system, we have got back rake angle, which is also called side rake angle, back rake, which is also called top rake. So back or top, back rake angle, and we have got top rake angle. Then we have got side rake angle. Then we have got end clearance angle. Then we have got side clearance angle. Then we have got end cutting edge angle and side cutting edge angle, which is the primary cutting edge angle. Remember, side is the primary one in the turning, and then there is a nose radius. We have another system, that is orthogonal rake system. I told you it is based on 3 particular planes: reference plane, cutting plane and orthogonal plane. It is also called continental system. In this, we have got inclination angle. That means it shows the inclination of the cutting edge, and then we have got orthogonal rake angle, that is in the orthogonal plane. Then we have got principal frank angle. Frank is basically same as the relief angle, you can say principal relief angle. So frank means it is basically the surface side. And then auxiliary frank angle on the auxiliary face, then auxiliary cutting edge angle, and then principal cutting edge angle, and nose radius is there. Then we have one British system also, that is called maximum rake angle. See, if something is inclined in 2 directions, this plane is inclined this way, and as well as other way. That means there is a slope, suppose in x direction, there is a slope in y direction also. There is a slope in the feed direction, there is a slope towards the radial direction also. Then there will be one particular slope that will be having maximum slope of that surface. So in that plane we find out maximum rake angle. Suppose side rake angle is 5 degree, top rake angle is 10 degree, then maximum rake angle will be something maybe in between 5 and 10. Then oblique plane angle, that means in the normal plane we show that is called normal and maximum rake angle, and then we show oblique plane angle, then we show principal flank angle, auxiliary flank angle, relief angle, auxiliary cutting edge angle, then we show principal cutting edge angle, and then we show nose radius. Nose radius is common in all these things, that is the 7th element. Then we have international system, that is normal rake angle. Here we show inclination angle, then we say normal rake angle, that means rake angle in the normal plane. I already told you what do you mean by normal plane, that is normal to the cutting edge. You have cutting edge, just take one plane normal to the cutting edge. Then we have got principal flank angle, then we have got auxiliary flank angle, we have got auxiliary cutting edge angle, and we have got principal cutting edge angle, these and nose radius. So here in ORS system again tool signature is like this. This is we have got inclination angle. So I am showing you here. Let me just move my cursor up. Here this is I, inclination angle I. Then we have orthogonal rake angle. Then we have principal flank angle by delta P. Then we have auxiliary flank angle denoted by delta A symbol. Auxiliary cutting edge angle. Then principal cutting edge angle, that is main cutting edge, and then you have got nose radius. So this is in ORS system. In ORS system, I am showing that this diagram, it is because things are 3-dimensional, so one can easily understand by means of taking various views, orthogonal views. That's how we understood for SA system. So you will be able to understand for this system also. In the ORS system, if I just show the top view of the tool, this is the top view of the tool. So in the top view, what you are seeing, that in the top view, you are seeing that nose radius. This is the nose radius. You are seeing this is the auxiliary cutting edge angle, and you are seeing principal cutting edge here. So auxiliary cutting edge is angle between the feed direction and this edge on the top view. So you are having auxiliary cutting edge angle, and principal cutting edge angle is what? It is the angle between the feed direction and this cutting edge. So that is why it is principal cutting edge. And now, so in the top view, you have seen these two angles. Now what I should do that here, if I take a orthogonal plane, that means we told you, or before that you can understand that if I take a cutting plane, that means which is containing the cutting edge. So I cut it like this, along this, like this. So you see that this edge from the sharp point of nose, it is just leaning back. So that means it is at some angle, and from the top reference surface, that means this is perpendicular to the velocity vector. So from here, that inclination is called inclination angle. That means this is this one. If it was orthogonal cutting, then inclination angle would have been 0, and in that case cutting edge would have been really this. That means this dotted line in that case would have been cutting edge, because the velocity vector was vertical here in this direction. So both these were orthogonal to each other, but in this case what happens, velocity vector is in this direction only, but this cutting edge is actually really inclined in the cutting plane in this manner. That is why you are getting inclination angle. So in the orthogonal, in the cutting plane, you are getting one angle that is called inclination angle. So out of 6 angles, now you understand 3 angles here. Now take the orthogonal plane. which will be perpendicular to the cutting plane as well as the reference plane. In that orthogonal plane, you are seeing that this surface is leaning down, rake surface, so which gives you orthogonal rake angle. The rake surface is leaning backward, and similarly other frank surface is also leaning in this direction from left to right, and this angle is called principal frank angle or principal relief angle. So this is visible in the orthogonal plane. You are getting principal frank angle and you are getting orthogonal rake angle. You have seen here 2 to 4 and 5. Now you will see one more angle. This is auxiliary cutting edge angle. If I cut a auxiliary orthogonal plane, that means here I have made a orthogonal plane based on the cutting edge, and here similarly I cut it here orthogonal plane which is orthogonal in this direction, then you are seeing that here that surface is inclined, frank surface is inclined, and that is called auxiliary frank angle. That means frank surface is really down, that is called auxiliary frank angle, somewhat similar to the end relief angle in SA system. So that is the type of thing. And in wireless system, you are seeing that principal cutting edge angle is basically nothing but 90 minus side cutting edge angle, because there we defined side cutting edge angle as this, and here I am defining like this. So this way we have shown these are the various angles in the orthogonal system, rake system. So this also, I hope that now this point is also clear to you, orthogonal system. Now we go to this one, MRS system. In MRS system, maximum rake angle system, you will have again 6-7 elements of the tool signature. First one is the maximum rake angle, alpha m. Another is oblique plane angle, and then the third one is the principal frank angle, and the fourth one is the auxiliary frank angle. Then you have got auxiliary cutting edge angle, and then you have got principal cutting edge angle, and then you have got principal cutting edge angle. After that you have got nose radius. So this is called maximum rake system. In this, which is also called British system, how do we designate the angles? Just see that. Let us go in the same way, one by one. Top view, this is the reference plane. Like in oblique cutting system, like in orthogonal cutting system, here also you are getting principal cutting edge here, auxiliary cutting edge here. So you are getting principal cutting edge angle theta p. This is principal cutting edge angle, and this is auxiliary cutting edge angle. And then we have got, now we have to understand various things. Now if I say maximum rake plane is this, so I have cut it in this direction. This is the maximum, this is called oblique plane. This is somewhat oblique, but in this particular plane, if you cut a section like this, your rake angle will be maximum, and that is designated here, that is alpha m. So that system is there, and in this direction, if I go to this one principal in one orthogonal plane, in orthogonal plane I am getting principal frank angle. So orthogonal plane view is also shown. This line plane I have taken along this orthogonal to the basically cutting edge direction, side cutting edge direction, or principal cutting edge direction, and you are getting that principal frank angle in the same way. Then similarly I take a orthogonal plane considering this as a focus, that auxiliary cutting edge, then we get auxiliary orthogonal plane, and here also I am getting auxiliary frank angle, and I am getting this one. This oblique plane angle is basically theta m, it is defined here. So if we see that we need one oblique plane angle, that means really that particular plane in which the rake angle is maximum, how much it is inclined with this direction. So that will give theta m, which will give theta m, and that is what that also you have to specify. So you have understood that maximum rake system also, and now we discussed NRS, that means normal rake system. In the normal rake system, you have got inclination angle, then you have got normal rake angle, then you have got principal flank angle or relief angle, and then you have got auxiliary flank angle, then we have got auxiliary cutting edge angle, and then we have got principal cutting edge angle, and then we have got nose radius. Nose radius is also there. So this one we have already shown, and this one we now have to understand in this diagram. So here again you make the top view in the same manner. You get a side cutting edge here. This is the side cutting edge, and then here it is end cutting edge. You are, as usual as in all the systems, you are getting principal cutting edge angle, which is basically in SA system it is 90 minus side cutting edge angle, and then you are having auxiliary cutting edge angle. That means this is also principal cutting edge angle, and you can have that direction here. You can define auxiliary cutting edge angle in this way. That means from here how much it is inclined. Okay, if you take a 90-degree line here, so you have auxiliary cutting edge angle and you have got principal cutting edge angle. And then if I take a plane, cutting plane, this is the cutting plane like we did in the orthogonal system. So this plane is the common, and in this particular plane we have got inclination angle. This is inclination angle I, and if I cut it, this one some plane normal to the cutting edge, then you get another plane that is called normal plane. On this plane whatever is the angle, that you are designating it by normal rake angle. So that type of system you have done. And on the auxiliary, I can obtain, like I have obtained a cutting plane here in which the cutting edge is contained and the velocity vector is contained. Similarly, I can obtain one particular plane which is called basically the auxiliary edge. So auxiliary edge is contained in that, velocity vector is contained in that. So we get a auxiliary cutting plane, and if I cut it perpendicular to that auxiliary edge here, we get basically auxiliary normal plane, and in the auxiliary normal plane I can get auxiliary flank angle. Of course, I can get auxiliary rake angle, but that is not specified here. We have specified this one normal rake angle, so we get auxiliary flank angle, and this way we can define it for in RS system, that is normal rake system. So I have told you now 4 systems of tool designation. ASA, we commonly use ASA system, very easy to understand, and orthogonal, most of the books in metal cutting literature, they may use orthogonal rake system also, or even normal rake system also. Maximum rake system, which is a British system, is not in much use either by research community or by practicing engineers, but I have told you that system also, that in which designation is based on a plane in which the rake angle is maximum. That also has been explained, and this one will. Okay, so NRS system has been explained, MRS system has been explained. Now, in this slide, we will discuss that what are the effects of the various rake angles based on textbooks that I am explaining. Rake angles, whether it is side rake angle or it is the top rake angle, basically it controls the direction of resultant force. It also influences cutting force, power, surface finish. In general, higher is the rake angle, lower is the cutting force. That means if you increase the rake angle, your cutting force decreases. Accordingly, the power also decreases. Surface finish improves. That means if you give more amount of rake angle, chances are that surface finish will be better, that will be there. then larger is the rake angle, lower is the cutting force, lower is the power and better surface finish. Higher values of rake angles are used for softer materials, because softer materials anyway will be easy to machine, they do not offer much resistance, so not much forces are generated. Then why we want more rake angle to further reduce the force? No, objective is not to reduce the force. Actually, if you increase the rake angle, as I told, the tool becomes weaker, no? Because less amount of included angle is available. So that I have already explained. Now since they are soft material, no problem, even if little bit tool is weak also, but in the harder materials you have to give that rake angle, particularly if the material tool is cutting tool material is very brittle and it may break under the impact, like carbide tools. Most of the carbide tools are given negative rake angle. Here higher value of rake angle are used for softer material, so that continuous chips will be generated and they can easily flow on the surface. In general, harder is the work material, the lower is the rake angle. If the material is harder, then you give the lower rake angle. So rake angle generally varies from 5 degree to 15 degree for aluminum. Mostly this data is for HSS tool. This is high speed steel tool. This you are seeing that high speed steel tool. In this we are showing these things. So it is rake angle may vary between 5 to 15 degree. In the carbide the angle may be somewhat smaller, 8 to 12 degree for steel, and we can have 5 to 10 degree for cast iron. These are this one. As I told that exact what should be the proper angle, that has to be either scientifically optimized, otherwise people do it by experience, and by experience they understand that this particular amount of rake angle will give me good result, and that is what. Then flank angle. Flank angle means relief angle, or it is also called clearance angle. Different books may use different type of words. So this is relief angle, or it can be also called clearance angle. So it is provided to clear the sides of the tool so that it doesn't rub. They do not generally affect the cutting force. Cutting force, there is not much effect on the cutting force, but larger flank angle will rub less but make the tool weaker. If we make, this is a tool, this is rake face and this is flank face, if I increase this angle, this portion becomes very small and it becomes weak. So for HSS and carbide tools, the values of these angles are in the range of 5 to 12 degree and 5 to 8 degree respectively. That means HSS tools mostly have 5 to 12 degree, but carbide tools generally have less amount of the relief angle, and that may be about 5 to 8 degree. And larger values of flank angles are used for tougher materials. That means which do not cause much impact. They are tougher materials, they can absorb a lot of amount of energy, and smaller values are used for brittle tool materials. Suppose tougher materials, tougher tool is there, we can afford to give it larger amount of angle, even though it is little bit weak, doesn't matter because it can absorb shock. But if the tool material is brittle, like in carbide tools, then in that case you have to give that small amount of that angle. And cutting edge angle is provided to protect the cutting edge from rubbing against the surface, and it reduces the tool chatter. Chatter means self-excited vibrations. It also has effect on that, and it affects the tool life and surface finish. So cutting edge is also this one. If you make that straight cut like this, then less amount of area is there, more temperature increase will be there. But if I do oblique cutting, then more surface area is there, temperature generation may be less, and it is very convenient. So cutting edge angle is also important. Cutting edge angle, large amount of cutting edge angle may be provided, and This is what so effect of the cutting edge angle. So all these things have to be optimized. You go to the lathe machine shop or machine shop, you see the lathe machine and try to understand these various type of angles and what is their significance. You will get practical feel about that. You touch the tool by your hand and see and try to understand that 3D geometry. Next lecture I am going to tell you about that how these angles are related with this one and that one. So here typical tool angles in ASA specification for single point turning are shown. Suppose workpiece material is mild steel, tool material is HSS, cemented carbide, brazed one, then throwaway tips can be there, that machine and throw away that tip. So these are the tool angles in degrees, back rake angle, side rake angle, then this is end relief and side relief. You are getting all these values 8, 10, 5, 5, brazed one may have 0, throwaway type of thing may be having rake angle size negative. You see that negative rake angles are here. And then suppose we go to cast iron. Cast iron, in that we are machining by high speed steel, then this is cemented carbide, brazed and throwaway. So here you see in cast iron machining also I am having more or less positive rake angle in high speed steel, but it becomes negative in case of throwaway tips etc., maybe tungsten carbide tips or something, and clearance angles are almost, relief angles are almost same, 5 degree or something. Aluminium alloy, aluminium is naturally much soft material, so therefore HSS will angle tool may have back rake angles or side rake angles to the tune of 15-20 degree, and throwaway tips may have 0 or some positive angle we can afford. And here these have been shown here. Stainless steel is a little bit hard material, so here even in HSS I am giving the 0 angle, this is 0, then here it is a side rake I have given some 10, but here I have given -5, -5. Then tool steels in this HSS is -3, and then we have 10, and brazed one is of course negative, and you see that side clearance are about 5 degree or something. These are just the typical values. That means these things are in the same way it is going. You have to, it is based on the experience, you have to see lot of data base, and there is always a scope for improvement and do much research on that. So no problem that, but typical values, so that you should get a feel. You should not say my top rake angle is 30 degree or it is say 60 degree. You should get a realistic feel. That is why I have shown the table, not that this table you have to memorize and you have to consider it as a guideline or something. So this I have explained, and in the next lecture I am going to tell that how the angles can be converted from one system to the other system. So to summarize, let me just glance through that. I have told you about the rake face and flank face. This is very important for you to understand about the rake face and flank face. Then I have told about the flank wheel, Prater wheel, we will discuss in detail. I have shown a typical lathe tool 3D diagram. This diagram you should be very familiar with this, and always we make the 3 views of the tool in the SA system, then very easily we can show all the related angles, and in the workshop that operator he grinds the angle accordingly. Even if your tool gets worn out, then grinding can be done. That operation is done there. In ASA tool system, we have told the tool signature. There are tool is designated like this, and this last digit is basically the nose radius. This ASA tool signature system we have told. We also told that how we take the reference planes based on which we measure. So we told you oblique or normal reference system, and we also told orthogonal reference system. We told that what is the effect of the height of the tool on the rake angle. Then we have told 4 type of tool nomenclature system. We have told ORS system, then we have told MRS system, maximum rake system, that is British system. ORS system is called continental system, and then normal rake system is called international system, that is international system means NRS. In that also we have shown normal rake angle, and then normal rake angle and orthogonal rake system is somewhat similar, not much difference. Of course, the normal rake will be slightly different from orthogonal rake. If there is a inclination angle of the cutting edge is there, then it will be like this, but and this can be, but generally inclination angle is not very high. So most of the times you will find out practically the normal rake angle is basically same as the orthogonal rake angle. Okay. And then I have told you this means how we decide to make a rake angle, what is positive point about the rake angle or this thing. I hope that you have understood what is our sign convention also. The way I have shown the pictures, these angles are positive, in the other way they will be negative. That means easy flow of the chip, that means the rake angle is positive we define, otherwise it becomes the negative. And this one, then I have shown the typical tool angles. This was the last slide, and with this today's lecture is over. We will be going to the next lecture.